The 4.1 notes focus on diffusion, and this is the first section of notes in Unit 4, which focuses on homeostasis and the cell membrane. For this section, make sure you read pages 97 to 102 in your textbook. We're first going to talk about the concept of maintaining homeostasis within a cell. Cell membranes, which we learned about, are phospholipid bilayers in the last unit, help organisms maintain homeostasis by controlling what substances may enter or leave cells. Passive transport is the type of cellular transport where substances can cross the cell membrane without any input of energy. Some common examples of this are diffusion and osmosis. This particular section of notes will focus more on diffusion. We'll talk about the osmosis of water at another time. In the diagram below, you can see is a diagram representing the phospholipid bilayer here in blue. Notice that the membrane controls the diffusion of the red particles into the cell. Let's focus more on that concept by taking a closer look at diffusion. Diffusion is actually a result of the natural molecular motion we see in molecules. Molecules are in a constant state of motion because they have kinetic energy. If you think back to physical science, kinetic energy is the energy of motion. The molecular motion that results from kinetic energy is random. So the net result is that molecules tend to move from areas where they are more concentrated to areas where they are less concentrated. I'm going to load up a demonstration on the screen here that's going to show the movement of a dust particle in relation to the gas molecules around it. Notice in this diagram, this little Java applet, notice over here, this is supposed to blue, over here this little blue dot is supposed to be a dust particle. If we zoom in at the molecular level, the dust particle is being bombarded by gas particles. So the random movement of that dust particle is a result of the random motion of the gas particles that are colliding with it. Overall, this will result in the diffusion of substances that are more concentrated to areas that are less concentrated. This is known as diffusion. So again, the diffusion is called or defined as the movement of molecules from an area of higher concentration to an area of lower concentration. A concentration gradient is the difference in the concentration of molecules across a distance. So in this sense, we can say that molecules tend to move down their concentration gradient. Diffusion continues until all the molecules are said to be in equilibrium, or in other words, there's no longer a concentration gradient. So equilibrium is the concentration of molecules will be the same throughout the space that the molecules occupy. Here's another demonstration where we're going to focus more on diffusion across the cell membrane.
Substances that can pass easily through a cell membrane do so by the process of diffusion, which is the movement of particles from an area of higher concentration to an area of lower concentration until the concentrations are equalized. In this beaker, we have two different substances dissolved in water, separated by a semi-permeable membrane. The initial concentration of substance A is high on the left side of the beaker and low on the right. The concentration of substance B is high on the right and low on the left. In this example, substance A and substance B diffuse across the membrane from an area of high concentration to an area of low concentration for that substance. Each substance moves down its concentration gradient. Eventually, equilibrium is reached, where the two sides have equal concentrations of substance A and substance B. The molecules continue to move across the membrane, but at equal rates.
Moving forward, we can talk about the different kinds of diffusion. Simple diffusion is like what you just saw in that demonstration. It is the diffusion of substances across the cell membrane without the help of membrane proteins. However, some molecules cannot readily pass through the phospholipid bilayer of the cell membrane. So in this case, they need a little bit of help. And we call this facilitated diffusion, which is the movement of molecules across the cell membrane that is assisted by specific proteins in the membrane. Facilitated diffusion is used to move large molecules such as sugar, but also polar molecules and ions. Carrier proteins are the proteins within the cell membrane that are used in facilitated diffusion. The model of how carrier proteins work is depicted in the diagram below. In the first step of this model, a molecule will bind to the specific carrier protein. This forces the carrier protein to change shape, which eventually leads to that molecule being released inside the cell. Once the molecule is released, the carrier protein returns to its original shape and is ready to bind to another specific molecule. Take a look at this demonstration on facilitated diffusion.
Cell membranes are composed of phospholipid bilayers with interspersed proteins. Some amphipathic proteins span the membrane. Amphipathic proteins have polar and amino acids, which are hydrophilic, exposed to the membrane outer surfaces. They also have nonpolar amino acids that are stable in the hydrophobic interior region of the membrane. These membrane proteins serve multiple functions. Recall that membranes are semi-permeable. Molecules such as water and oxygen readily diffuse through the membrane, while larger molecules and ions cannot cross the membrane by simple diffusion. Yet ions such as sodium, chloride, and potassium, and large molecules such as glucose are vital to cells. Without the ability to diffuse directly, ions and large molecules move with the help of membrane proteins. Biologists refer to this type of transport as facilitated diffusion because the protein merely facilitates passage across the lipid bilayer. It is a form of passive transport because it does not require an expenditure of energy. Because ions are electrically charged, their movement is affected by any charge difference across the membrane as well as by any concentration difference. These two factors, difference in electrical charge and difference in concentration, determine the electrochemical gradient. Ions move spontaneously down their electrochemical gradient. In this example, sodium and other positive ions cross the membrane by passing through channels in a membrane protein, moving down their electrochemical gradient.